If there exists a one-parameter family of symmetries of the action, then any solution of the Euler-Lagrange equation has a conserved quantity. Let's now apply this to a physical system. Let's consider a system of n particles, x1, x2, and so on. Our curve Q will now contain the paths of all n particles in our system. We will also assume that our Lagrangian does not depend on the positions of the particles, but instead depend on the differences in any two particles' position. Now let our map Q take each particle's position to xi plus sa for an arbitrary vector a. This has the effect of translating our system in the a direction, by a distance depending on s. Clearly this will have no effect on the relative distances between any two particles, as they both get shifted by the same amount, sa. Our Lagrangian is unchanged on the Q. This means the action must also be unchanged on the Q, so Noether's theorem applies. But what is the conserved quantity? Well, dqi by ds at s equals 0 is just the vector a, so it reduces to this vector expression. But what are these terms? If the only term in L depending on xi dot is the kinetic energy, then this becomes mxi dot, the momentum of the particle I, so this sum is just the total momentum of the system. Since our vector A was arbitrary, this tells us the sum of the particle's momentum must indeed be conserved.